So next let us look at some examples of ring homomorphisms. The first example is quite trivial, nevertheless it's an example. Let R and R prime be two rings, any two rings. Define a function phi from R into R prime like this. Every element A of R is mapped onto the zero element of R prime. Then it's very easy to check that this is a ring homomorphism. In fact, we can do this quickly. If we take say two elements A and B in R, then phi of A plus B, by definition this is nothing but 0. That is the zero element of R prime. We use the same symbol to denote the zero element of both R and R prime. And this can be written as 0 plus 0, which is again phi of A plus phi of B. So phi respects addition. Like that, we have phi AB equal to 0. This also can be written as 0 times 0, which is phi of A, phi of B. So this says that phi is a homomorphism. And we can write it like this. Trivially, phi is a homomorphism. In fact, it has a name. Phi is known as, or we should not write it like that, is called the zero homomorphism. Actually, there is a reason for this name. If we collect all homomorphisms from R into R prime, that collection itself is a ring with respect to an addition and multiplication. We will come across that. In that ring, this is the zero element, this particular function. So that's why it has the name zero homomorphism. Okay, so let's go to the next example. Let R be any ring. Define a map phi from R into itself by defining phi of A to be equal to A. That means here every element in R is being mapped onto itself. And note one more thing, that here the domain and range are the same. It's easy to verify that phi is a homomorphism. Just like the previous example. Oh, and one more thing I forgot. Sorry about that. Is a homomorphism. I can write it here. We also have, we did not say what the kernel of the homomorphism is. I phi. Recall that by definition, the kernel of a homomorphism is the set of those elements in R which are mapped onto the zero element in R prime. Since here every element is being mapped onto the zero element of R prime, so the entire R is the kernel. So it's the largest possible kernel. Here, however, in this case, the kernel is the smallest possible. It consists of only the zero element in R. Okay, so these are two extreme cases. And the fact that this is a homomorphism can be verified in much the same way that we did in this case. Okay, then in the next example, these two are somewhat trivial homomorphisms. The next one is not trivial, and we will see. In the next one we have to work out the things. Let me write it here. J root 2, this is a symbol, be the set of all real numbers of this form where m and n are in the set J. Recall that by capital J we are denoting the set of integers. In Herstein's book, this is what the set of integer looks like. That's what denotes the set of integers. Usually, it is more frequently denoted by this blackboard bold Z. Instead of that, we are using J here in this book. So this is just a symbol denoting the fact that root 2 is somehow involved in this set. And this set is defined to be the set of all real numbers that look like this, m plus n root 2, where m and n are integers. All such real numbers. Okay. So the first job we have here is that we will prove that J root 2 is a ring with respect to ordinary addition and multiplication of real numbers. So let's do that first. Then we will come to homomorphism. Let m1 plus n1 root 2 and m2 plus n2 root 2 be two elements in J root 2. Then what about their difference? This can be written as m1 minus m2 plus n1 minus n2 times root 2. Now look at this. Because these are elements in J root 2, m1, n1, m2, n2, these are all integers. So m1 minus m2 is an integer, and so is n1 minus n2. That means this number again has the form to be an element in J root 2. So that's why it belongs to J root 2. Now what this tells you is that J root 2 is a subgroup of the group of real numbers under addition. And why is that so? That's because you see, recall from group theory that if you have a non-empty subset H of a group G, and you take any two elements H1 and H2 in H, and if you are able to show that H1, H2 inverse also belongs to H, then according to a result in group theory, H is a subgroup of G. That same thing we are doing here with J root 2 in place of H, and in place of G we have the set of real numbers. Actually not just the set of real numbers, but the set of real numbers with the binary operation addition. So here we have shown that this element belongs to J root 2, where these two are any elements in J root 2. And keep in mind that In the additive group, if I write this element m1 plus n1 root 2, m2 plus n2 root 2 inverse. This is the notation in a general group. In additive group, this same thing looks like this. m1 plus n1 root 2 plus minus of m2 plus n2 root 2, because in the additive group, the inverse of m2 plus n2 root 2 is minus of that, and the binary operation is addition. So that's what we have done here, and as such, j root 2 has now become a subgroup. Hence, j root 2 is a subgroup of the group of real numbers under addition. So being a subgroup, it's a group in its own right under addition. Okay. Also, okay, now we come to the question of multiplication. We multiply these two elements, and by multiplication we mean ordinary multiplication of real numbers. So if we multiply these two things, what do we get? After multiplying out term by term and after collecting common terms, we get something like this: m1 m2 plus n1 n2 and root 2 will become 2. n1 n2 plus m1 n2 plus m2 n1 root 2. Now look at this final number. m1 n1 m2 n2, these are all integers, and here we have 2. So that means this is an integer, and this thing inside the brackets is also an integer. So that means this number again has the form to be in j root 2. So that's why it belongs to j root 2. Okay, so we have proved that j root 2 is a group under ordinary addition, and it is closed under ordinary multiplication. What else is true? Ordinary multiplication is already associative, and it distributes over ordinary addition. So that means we have shown that j root 2 is a ring with respect to these two operations. So we can write that since multiplication of real numbers is associative and it distributes over addition of real numbers. I need ink. Okay, give me a minute. So it is associative, we already know. Actually we don't know, but we are assuming that we know, since as yet we have not developed the system of real numbers. I am talking about our analysis videos. But anyway, we assume that we know that real numbers and all their properties are given to us. So multiplication of real numbers is associative and it distributes over addition of real numbers. j root 2 is a ring under these two operations. So we now have the fact that j root 2 is a ring. Now we can use it to define a homomorphism. Now we are going to define a function whose domain is j root 2 and whose range is also j root 2, and the function is defined like this: m plus n root 2. That's how a typical element in j root 2 looks like. The image is defined to be equal to m minus n root 2. Note that m minus n root 2 is again an element in j root 2 because the components, if we call them components, m and minus n are again integers because m and n are integers. So that's why this function is a well-defined function. We now claim that this is a homomorphism. For m1 plus n1 root 2 and m2 plus n2 root 2 in j root 2, we now verify that this is a homomorphism. The part involving addition is quite easy. We have to add these two elements and then find their phi image. So according to the definition, we have a minus sign here. That's the image. m1 plus m2 minus n1 plus n2 root 2. So this becomes m1 minus n1 root 2 plus m2 minus n2 root 2. And this is nothing but phi of m1 plus n1 root 2, and this one is phi of m2 plus n2 root 2. So this tells us that phi respects addition. Now we look at the multiplication. And multiplication is relatively more complex than addition, but it's not unmanageable. We can manage it. m2 plus n2 root 2. So first we calculate the product inside. In fact, we have already done it once. m1 m2 plus 2n1 n2 plus m1 n2 plus m2 n1 root 2. m1 n2 plus m2 n1, yes. So that means the image will be this: n1 n2 minus m1 n2 plus m2 n1 root 2. Okay. Now we have to verify that this ultimately is equal to this product. Times m2 minus n2 root 2. Let us see if that is the case. m1, m2, we have it here. Minus, minus, they become plus. n1, n2, root 2 becomes 2. So that means 2 n1, n2. We have it here. m1 times minus n2 root 2 gives me minus m1 n2 root 2. Like that, m2 times minus n1 root 2 gives me minus m2 n1 root 2. So this is okay. And this is nothing but phi of m1 plus n1 root 2 times plus n2 root 2. So that's why phi is a homomorphism. Hence, phi is a homomorphism. Now comes the question of kernel of phi. Should I do this? Okay, let's do it. Since we are working out this whole thing, let's do this one also. Let m plus n root 2 be an element in the kernel of phi. Then m minus n root 2, which is nothing but the phi image of m plus n root 2. This has to be equal to 0. Okay? By definition of kernel. And hence, and from this, what do we get? M is equal to n root 2. Now, if n is not equal to 0, if n is a non-zero integer, then we can divide both sides by n. And doing so will give us m by n is equal to root 2. But m by n is a rational number. By this we mean the set of rational numbers Q. And we know that root 2 is not a rational number. We assume that we know this, okay? And the proof is really easy. So we have, or we can write directly like this. So we cannot have n not equal to 0. So n should be equal to 0. But if n is 0, this right hand side is 0, that means m is also 0. But then m is equal to 0. Hence, the kernel, okay, so if both m and n are 0, then this is nothing but the number 0. So the kernel of phi consists of only the 0 element. So in this case also, just like the previous example, the kernel is the trivial set consisting of only the 0 element. Okay, so now next we look at the fourth one. The fourth one I think is, it's that one, okay. Let n be a positive integer, define the function phi from j into jn by this phi of a is equal to this, where this is the congruence class modulo n that contains the integer a. So recall from our discussion on integers, that very first thing we had, there we came across this set, the set of all integers modulo n, where n is some given positive integer, and actually jn looks like this. It consists of n distinct and in fact disjoint congruence classes. So this is our jn, and j is the set of ordinary integers. So an integer is being mapped onto the congruence class which contains it. We also know from our previous discussion that not only are these congruence classes mutually disjoint, if you take any two of them, two different congruence classes, then they are disjoint. There is no common point between them. But their union is also the set of integers. We have this, where I varies between 0 and n minus 1. We also have this. So if we have a, some integer given to us, then that a will belong to some congruence class. That congruence class is defined to be the image of a under this map. So one thing is there, one thing we can immediately see from this is that the images that we get in this map are actually elements in Jn. That part is okay. But we still have to, if we want, we can write something about the well-definedness of this. Okay, let's go through that. Instead of just saying things in the air, let's actually write the things. For a given integer a, there exists exactly one congruence class modulo n that contains a. Why? You see, because just now we have said that the set of integers is the union of all the congruence classes. That means if I take any integer, it will belong to some congruence class. But at the same time, so that means there exists some congruence class which contains this integer. But there cannot be more than one such congruence class. Why? Because the congruence classes are mutually disjoint. So they cannot have any element in common. So A cannot simultaneously be in two different congruence classes. That's why this congruence class which will contain A exists and is unique. And that's why this function phi is well defined. Hence, phi is well defined. If you remember, we have already gone through the videos on function, and if what a function does to an element in the domain is that it maps it to a unique element in the range. So this uniqueness is very important, otherwise the function is not well defined. Okay, so this is well defined. Now how is this a homomorphism? That is really easy, it's not difficult at all. But before that, you note the fact that this is also a ring, okay, with its own addition and multiplication, which we already know. They are the addition and multiplication modulo n for the congruence classes modulo n that we have already defined. So this is a ring, this is a ring. Now we have to show that this is a homomorphism. So let a and b be any two integers, then phi of a plus b is what? The congruence class containing a plus b. But according to the definition of addition in this ring, that is addition modulo n, this is nothing but this plus this. Note carefully that this is the addition in Jn, and this is ordinary addition between the integers a and b, and this is nothing but phi of a plus phi of b. And just like that, phi of ab is the congruence class containing the integer ab, which is nothing but this, and this multiplication is multiplication modulo n. So it feels like the operations in Jn have been defined in such a way that this becomes a homomorphism. Actually, that's the case. Okay. Now, so this means that phi is a homomorphism. Now we have to check we have to find the kernel of phi. Hence, phi is a homomorphism. And this one I will not do in detail. It can be easily verified that the kernel of phi is equal to the set of all multiples of n, the set of all integer multiples of n. If you take an integer multiple of n, then the congruence class containing that multiple is the class that contains 0. Okay, for example, if you take say 2n, okay, suppose my a is 2n, then what is phi of 2n? Phi of 2n is the congruence class containing 2n, but that is also equal to the congruence class containing 0. Why? Because 2n is congruent to 0 mod n. That's why. Or in other words, 2n is divisible by n. So that's why all the integer multiples of this fixed number n belong to the kernel of phi. Conversely, every element in the kernel of phi has to be an integer multiple of n. So that's why these two things are equal. That is the kernel. If you want, you can write it in detail. In fact, I want you to do that just as a nice exercise. Okay. Now we come to the fifth one. the fifth one involves functions. Let R be the ring of all continuous real value functions on this unit interval, closed unit interval. So that means the elements in R are functions that look like this. Functions whose domains are equal to the unit interval and whose range is the set of real numbers. And not just that, they are continuous. Okay, where we are following the ordinary definition of continuity. At every point in this domain, the function is continuous. You already know what continuity means. Now, this is a ring with respect to what actually? We should write that, isn't it? Okay, it's better to add that with respect to